Hi, everybody, and welcome. Thank you for welcoming us at the DataX Day. So I'm Jade, and today I'll be giving the talk with Alexis, and we'll be talking about multilingual sentiment analysis and emotion detection on social media data. And we'll also focus on how we are productionizing our deep learning model to perform this at scale. So we'll start with a brief introduction where I'll explain to you what we do at Linkfluence. And then Alexis will introduce you with the different opinion mining tasks we'll be considering today. Then in the second part, Alexis will deep dive into the deep learning architecture we choose today. So don't be afraid, there'll be a little bit of deep learning architecture here, but don't freak out. Then I'll focus on how we productionize these deep learning models into our production pipeline, and we'll conclude with our key takeaways and the different perspectives for this project. So let's start. What are we doing at Linkfluence? We are helping global brands to leverage social media data and turn it into insight so that it would feed their marketing, innovation, and marketing strategy. Because by analyzing the conversation produced daily on the web, you can understand what are the consumption trends, what is being said about a product, a brand, identify key followers or maybe communities brands might be interested to work with. But social media data is massive and structured, so at Linkfluence we combine large-scale processing and artificial intelligence to retrieve and analyze this data in real time. Actually, this real-time constraint is pretty important for some of the use cases we've got for social media analysis, such as crisis monitoring or event or campaign tracking. So we've got to be real-time. To deep dive a little bit on our processing engine, it is summed up in this diagram in a quite simplified way. So our pipeline is ingesting a lot of data either through our crawlers or by connecting directly to the data vendor's API from a lot of different sources. Could be web, forums, social data platforms, and so on. All this data retrieved, that represents millions of documents per day, are then sent to our enrichment pipeline. And this is where we'll focus for this talk, because it's where all our machine learning algorithms are used to perform the inference part on the data to structure it and analyze it. Then all the data is sent to the indexation through Elasticsearch. And thanks to this index data, users at Linkfluence could browse the data, filter it, either through using the SaaS platform we've developed, that is called Radarly, or by accessing it through the API. So you can get all the analytics on your data through it. So let's focus on the enrichment pipeline. One of the pipeline we've got here is natural language processing. This pipeline is currently implemented into Apache Storm, and so it's running on the JVM, and we currently have more than 50 models into production. And this pipeline has to proceed between 1,000 to 2,000 documents per second. And all our inferences are done by CPU. So as machine learning engineers, we've got not only to focus on the performance for the prediction of our model, but to fully consider also the computational performance of our model to be integrated into this production pipeline with the constraint we have. Another challenge we have is the internationalization of this pipeline, because we are dealing with more than 60 languages into the document we're processing, and we have clients all over the world and to different markets, so we don't want to keep our analysis only in English. We want to cover the largest set of languages possible. So here is a brief overview of the context in which we are developing the algorithm, and now I'll let Alexis talk about the opinion mining tasks we'll be considering today.
Yes, okay. So today we are going to focus on two opinion mining tasks, the sentiment analysis task, which consists in document level classification within 4 classes, positive, negative, neutral, and mixed. The idea is to, based on a text, try to infer which sentiment the author of the post tried to vehiculate through this. And we will also focus on the emotion detection task, which is also a document level classification, but this time it's a multi-level classification. We try to infer what are the emotions that are passed in the text. So you can have, as you might guess, you can have several emotions in the same text. And we chose 7 classes: anger, disgust, fear, joy, love, sadness, and surprise. And as Jade said, we are not dealing with normal text like you can find in a book or on Wikipedia. We are dealing with social media data. And trust me, social media data, it's really, really dirty. It's because that's noisy user-generated content, and you can find word contractions, grammatical errors, special terms related to social media, such as hashtag mentions. So it's really hard to train a model based on this data, and you can't use normal datasets. You need datasets based on social media data. And we also have a multilingual problem, because we need to our model needs to perform inference on more than 60 languages, and we are processing different social media platforms or even blogs. So the text lengths might differ if you're posting on Twitter or on Facebook, for example. And that's also a problem when you want to develop machine learning models, because that's usually it's not the same whether you are on short text or whether you are on long text processing. And we also, as I said, datasets for social media data are rare, and even more for opinion mining. And the majority of these datasets that are available online are actually in English only. And when you want to find a dataset, for example, in Spanish, in Polish, it's quite harder. And that's what we will try to deal with today. But let's focus on what was the initial goal of this project. Why did we launch this project? The initial goal was to enhance the sentiment analysis algorithm that was in our pipeline, because it was starting to getting quite old. And we had to keep in mind that we had 2 major constraints. As I said, we need to perform opinion mining on ideally more than 60 languages on every social media platform. So we have here a multilingual challenge, and this is faced due to the lack of manually annotated data. And we have a second problem, which is we need to handle at least 1,200 documents per second without making our infrastructure cost skyrocket. Obviously, you can buy more machines if you want to put any deep learning model in production, but that's not really the mood of the company to have more money spent on machines. And so we've got a computational challenge, and when we started the project 7 months ago, we were thinking that recurrent neural network-based approaches, or the new approaches based on the transformer architecture, would not be a real solution, because it's really expensive and computationally intensive architectures. So let's focus on the approach we took. And the first question we had is, how do we leverage the lack of manually annotated data? And well, we were not the first who asked this question. And actually, we discovered that there was existing different techniques, either to try to automatically annotate millions of data, or to use distant supervision to build models in order that the models can learn useful text representation, and then you just use transfer learning to retrain your model on the target specific task. And for opinion mining, and more precisely sentiment analysis, Deryu and Teng proposed a method to automatically annotate millions of data for sentiment analysis. They used a predefined positive and negative emoticon or emoji set, because on social media data, you've got many posts containing at least one emoji or an emoticon. And the idea was, for example, if in the post I have an emoji that is smiling, then it's classified. It's automatically labeled as positive. And if I have an emoji crying, for example, it's automatically labeled as negative. And that's to build a large amount of data automatically. That works quite well. And that was our previous sentiment analysis model was built on this strategy. However, you can see that there is a big drawback here when you're posting sarcastic content, and the emoji you put in your sentence is actually to emphasize the sarcasm. And the model you trained based on this data set won't be able to detect any sarcasm. So more recently, Felbo et al. Presented a new approach and a new model called Deepmoji. And basically what they do is that they leverage the power of emoji to encode the sentence representation of a text, and then they fine-tune it on the specific opinion mining task. This was quite interesting, and that's why I will quickly develop their approach. So yeah, Deepmoji, so what did the authors do? Well, basically, they started by predefining a set of 64 emojis, and they extracted 1.2 billion of tweets that were containing at least one of the emoji that was in the set. And they extracting this emoji from the text, and they were labeling the text with the corresponding emoji. And then what they did, they pre-trained by LSTM with attention network, so recurrent neural network architecture, to predict an emoji probability distribution, like you can see here, based only on the text. And thanks to this way, they show that it encodes emotional context. And then so once they pre-train their model on the 1.2 billion data set, they fine-tune this model using transfer learning methods, actually the chainsaw method, which consists just in freezing you one layer by one layer in your model while retraining on the target-specific task. And why is that good? Because first, they achieved the state-of-the-art on 3 opinion mining tasks: sentiment analysis, emotion detection, and sarcasm detection. Yeah, that was before Bert's arrival, but we launched the project actually before Bert, so that's why we focused on this, this model. And the most important for us is that they showed that emoji can be used to encode the emotional context of a sentence through this pre-training method. However, we couldn't use this as a thing because it has 2 major drawbacks when you remember our challenges. First, our computational challenges. The training and inference time of this model was way too long. Not for the training. Training, okay, 12 days for one epoch, we can afford that. But the problem was the 50 milliseconds per input into the production pipeline. And this is absolutely not good for us, because usually we would like, for a model, the prediction time to be between 1 millisecond and 7 milliseconds. So you can see that's way too slow. And the second drawback concerns the multilingual challenge, because if you see this method, you can say, okay, but you still need a data set for each language, because you need to fine-tune the model on the target-specific task. So it doesn't resolve the multilingual challenge. However, we decided to take the good points of the very good points of this paper, and we decided we tried to develop an idea. And actually, it's a 4 steps idea resolve our challenges. So first, let's imagine that you can, being given a text, develop a model that will output an emoji probability distribution based on the content of the text. So this is exactly the Deepmoji pre-training phase. But let's consider that we can put a model that is computationally cheaper. And now let's imagine that we don't fine-tune this model. We just build a second model that will take the emoji probability distribution based on English language, and that will decode this emoji probability distribution into a sentiment, into an opinion mining task. So now we did that. Imagine that it's really easy for us to generalize, to retrain some models on French language, Spanish language, to output emoji probability distribution based on the corresponding language. And in an ideal world, we would like to generalize from this second model that was trained based on slowly emoji probability distribution based on the English language to generalize to other languages. So we would need only one data set here in this example, one opinion mining task data set to being able to infer sentiment for 3 languages. And that was the idea we tried to put in place. So first, we needed to find a new architecture for the model, as the LSTM with attention was not an option. We explored the different CNN architectures, and we found a new architecture which is actually a combination of attentive convolutions and the two-layer CNN architecture that was used by the Swiss cheese team winners of the Task 1A of Semeval 2016. It's an NLP competition. And so here is the model. I won't go into details for the attentive convolution architecture, but that just it's kind of adding an attentive context vector into your convolution operation. And so, okay, we built a new model, but we needed to benchmark it against the LSTM with attention to see whether the emoji prediction is still good compared to a recurrent neural network. So we benchmarked the two architecture on our own data. We took a data set of 512 million of English tweets. And for the CNN, the training time was only 44 hours per epoch compared to 12 days. But the most important was the predict into production, which was only 5 milliseconds per input against 50 milliseconds per input, which was 10 times faster. And when we look at the prediction accuracies, we can see that here our model that we call Unimoji performs quite well against the Deepmoji architecture, the Deepmoji pre-training phase. And we can see that it's even better on top 1 accuracy, but quite worse on the top 5 accuracy. So it's okay. This architecture performed as good as Deepmoji pre-training phase. But the real question is this learned sentence representation based on emoji can encode enough emotional context of a given sentence? That's really important. Actually, can we decode the learned representation by the CNN into to predict, to do an opinion mining task? And so we developed the second classifier here. So that's the step 2 of the idea. As we have only 64 features, the emoji set, we just took a 2-layer neural network, but you can actually take whatever you want, logistic regression, random forest, decision tree, whatever. And we compared the quality of the learned sentence representations, benchmarking over the Deepmoji approach, initial approach, against our new architecture CNN approach on the 4 opinion mining tasks. And when we look at the results, so here we've got on the first column the data sets, the metrics, And the first one is the real Deepmoji approach with the pre-training phase and the fine-tuning phase. So that's the kind of the state-of-the-art results. Then there is our CNN architecture that we fine-tune. Okay, so that's quite fair. That's quite even maybe a bit below, but it's actually quite the same results. And then we've got the two architectures that where we built the model upon only the emoji sentence representation, so with only 64 features. And when we look at the results, we can see that the representation learned by the pre-trained BLSTM approach and the CNN approach is quite the same. Okay? And when we compare these results to the original approach with fine-tuning, we can see that the results are quite below, because you're based only on an emoji representation and not on the whole text representation. But it's just quite below, and then it was acceptable for us, because we would be then able to verify whether we can do multilingual, we can generalize to multilingual opinion mining tasks. So yeah, the opinion mining task yields great results compared to the fine-tuning task. And one more thing now. Now we need to verify the most important. All the work we did would be nothing if this didn't work. So we needed to verify that the mapping that was learned by the emoji to task model, so the two-layer neural network, can generalize on a new emoji representation coming from text from another language, so from another model, other doc2emoji model. And why we assume that this would work? Because actually emojis are universal across all languages. Whether you're Spanish, whether you're French, I don't know, Polish, on the social media platform, you use the same base of emojis. And this would work if we assume that the context in which the emoji are used in one language and in another would be quite the same. Not all the same, but quite the same. This would work, we assumed. Okay, so how did we verify the approach? We trained three new doc2emoji models here in French, German, and simplified Chinese. And we took as the main language to train this model, we took the English emoji sentence representations. Why English? Because, as I said at the beginning of the talk, we have manually and reliable, manually annotated data sets for social media data in the English language. And we performed the experiments on two tasks: sentiment analysis and emotion detection. So first, for the multilingual sentiment analysis, we trained the emoji2task model based on the SEMeval 2016 task 4a dataset, which contains 3 classes: negative, positive, and neutral. And as we didn't have datasets in German and in Chinese, for example, we had to manually annotate data in the company, because you can find some other data sets for social media data in French, for example, but we found one that had 4 classes. And the classes were different from ours, so we could not really compare the approach between the different languages. And here are the results from the manually annotated data internally. English, French, German. There is a big improvement compared to our previous algorithm, around from 6 to 10 points of accuracy. So that was really nice for us. However, when we look at Chinese accuracy improvement, it's actually a big decrease, minus 30 points. And that's a real question. Why is that? Well, when we tried to guess why, we actually discovered that the context in which emoji are used in Chinese is really different from the context in which English people are using emojis. So, for example, a smiling emoji won't have the same meaning for Chinese people or for English people. And this is really a problem, and this shows actually the limitations of such an approach on representations that are too different. And however, we could annotate data internally, so we still could use the CNN that was pre-trained, and we could still fine-tune it, achieving around 90% of accuracy. Same for emotion detection, exactly the same, so I will go really fast on that. To train the emoji-to-task model, we took the SEMEVAL 2018 task 1 EC dataset, and we kept only 7 out of the 11 emotions that are in the dataset: anger, disgust, fear, love, joy, sadness, and surprise. Remember that it's a multi-label classification. And we also internally annotated data in English, German, and French. We dropped actually the Chinese as we knew it would not work. And here are the results. We compared with model trained from scratch to the on the annotated data online. And here are the results of our approach. English, the accuracy is around 80% on average, and we considered that as we didn't have this feature yet into the production pipeline, we didn't have emotion detection algorithm. So we decided that it was kind of free to put it into production. And to sum up, okay, so remember we had 2 problems. First, a computational challenge and a multilingual challenge. How did we deal with the computational challenge? Well, we created a new architecture, a new CNN architecture that is providing near a state-of-the-art result before BERT's arrival, and while being around 10 times faster compared to the original DeepMoji architecture. And how did we deal with the multilingual challenge? Well, we used a model per language to encode emoji representation, so emotional context given a text, and then we use just a light model based on that will decode emoji probability distribution into a target-specific opinion mining task. So actually, you only need one big model per language and one small model per task. And yeah, obviously, this is not perfect. It has limitations, such as the Chinese case that I presented to you.
OK, so now I'll go on the deep learning and production part. So as machine learning engineers at Linkfluence, we are taking our projects from the initial research and prototyping to the final integration into the production pipeline. And if you're working also on this frontier between data engineering and machine learning, you may also feel a little bit like this. You've got all these pretty cool frameworks for large-scale processing that are running on top of the JVM, Apache Storm, Kafka Stream, Apache Flink, and so on. But all the super cool frameworks for deep learning and machine learning are running on Python or C++. In our case, we also wanted to integrate this model into our production pipeline that I presented to you earlier. So to remind you, it's running on Apache Storm. We've got this near real-time constraint, and we've got a quite heavy throughput. So what are the solutions possible for us? Maybe this part will sound a little bit like the talk provided by Kai this morning. But when you're running on the JVM, you mostly have 2 alternatives. The first is to embed your model directly into your stream processing application, either by using TensorFlow Java API or Deep Learning 4J, which has a Keras model API, or directly using Deep Learning 4J, or using the H2O.ai framework. The other alternative is to embed your model and deploy it into a dedicated server. You can do so either by using TensorFlow serving framework, or you can do so by developing your own server using Flask and any machine learning model you want. But those two alternatives come with different trade-offs. The server deployment part is great for people who want to use any kind of machine learning toolkit they want. And it's also great when you're not familiar with stream processing application. Data scientists and machine learning that are just confident in using Python and don't want to go into Scala or Java, they're quite familiar with this environment. It will be easier for them to put their model into production. Also, if you have some model management challenges, you want to perform some A/B testing, or you want to put different versions of the same model into production, TensorFlow serving is providing great functionalities to do so. But this approach comes with major drawbacks. First, as Kai said this morning, it couples the availability and the scalability and the throughput of your stream processing application with the availability of your server. So this might not be super interesting for us. Another thing is it's way harder to deal with failures, because now you've got two different parts of the code to handle and to handle the interaction between them. So in our case, we went for the embedded option. And we didn't benchmark the H2O framework, but we tested the TensorFlow Java API and Deep Learning 4J API. But at that time, Deep Learning 4J wasn't so mature, so we went for the TensorFlow Java API, which was great. It enabled us to use directly in Java deep learning models that we pre-trained earlier in Python. So now that's great. We know how to put our deep learning models into production. But when you're using TensorFlow, actually, you can also go with some optimizations that are still beneficial when you're doing large-scale processing and you've got this near real-time constraint. The first of them is to optimize your TensorFlow build. And because most of the time, you might use the default binaries provided by TensorFlow. But it has been compiled to target the largest set of hardwares. And you might have some optimization available for you. And actually, TensorFlow is even warning you about that directly in the log of your application when using TensorFlow. And all you've got to do to benefit from that is to build TensorFlow from the source using Bazel and the appropriate flag. Another optimization is to use Intel MKL library to provide you with further optimization when running on CPU. The other thing to do is to optimize your graph model. When you've saved your model after training, you've got two separated files, your graph model and the weight of your model. By freezing the graph, you will first have one only file with the weights directly embedded into your graph as constant instead of the variables in which you load your graph. You load the weight, sorry. And also, another great thing that freezing your model is doing is it will remove all the parts of your model that are not used for forward inference. And so you will get rid of all the unused operation for inference. So you've got a faster and smaller model. If you want to go even beyond, you can use the optimization for inference script or the graph transform tool provided by TensorFlow, which will enable you to perform other optimization operations, such as removing debug operation, or even shrinking, optimizing some specific operation. And depending on the computational requirements you have, you might even be interested in quantization of the weight and of the node, which are other operations you can do to further decrease the size of your model and to get a faster model with just a little trade-off with the accuracy of your model in the end. So here was how we use TensorFlow in production in our Java stream application processing. And now we'll conclude with the key takeaways.
Yeah, so as I said, we developed a 10 times faster architecture based on CNN with small accuracy loss only. But the most important, I think, is the modular architecture that we call the DeepMoji that contains the two models, doc to emoji and emoji to task. And you can change the architecture, which shows CNN for our business purposes and our production constraint, but you still can use LSTM-based approaches, even more complicated or transformer-based approaches. And we also performed an improvement on our previous algorithm that was the initial goal of the project. And we developed, because of this idea, more thanks to this idea, we developed a new feature, the emotion detection, almost for free.
And from the technical part, this was the first deep learning model we put in production in our natural languages processing pipeline on the JVM. And by browsing all the resources available and all the great work of the community, we were able to find some optimization available to even boost our inference time and our computational speed on this.
Yeah, and what are the perspectives of this project? Well, obviously, we plan to add more languages. For the moment, we have 6 languages into production using slowly the English-based model. And we will also continue to explore the limitations of this approach. And because of that, we might not only focus on emoji, and we will explore cross-lingual models or even the new cross-lingual embeddings for social media data.
And we might be interested in getting further in this quantization, optimization, all this recent work on weight pruning to be able to use larger architecture with still our constraints that are in place. We might be also interested in enriching our pipeline with some kind of hardware mix between CPU and GPU, depending on the task we may want to solve. Also, we are pretty excited about the TensorFlow 2 that is coming, because maybe it could provide us with some interesting features for productionizing our deep learning models into production. Thank you.
Thank you.